talked about running in parallel on a cluster. So some of the differences between running in parallel on a desktop machine versus running on a cluster is that, as I mentioned before, we require additional parameters for the batch queue system. Another important point is we strongly recommend using our data writer HDF5 ext for external for output. And the differences between the data writer HDF5 and the data writer HDF5 ext is that in an HDF5 file, you can think of it as a database containing all the values. In the external, we have external data sets. So the actual raw values are written using MPI-IO, and so that's a separate raw binary file that just contains those values. The HDF5 file is essentially just a metadata file that is a database that contains sort of the names of values, how many values are being stored, sort of how many time steps, how many points, how many components, and then there's just a pointer to the name of our raw binary file. And the advantage of this is that if for some reason the simulation stops prematurely, we are much more likely to have an intact HDF5 file because it is written with our external data sets, because it is written by a single process, and it can be done very quickly with these pointers to the external data sets. Whereas if we are writing to an HDF5 in parallel, we're essentially writing to a database in parallel. If one process craps out, crashes, goes offline, or there's a problem with the disk, then the HDF5 file is likely to be corrupted. And then we can't look at any values within our HDF5 file because the database is corrupted. Whereas if we have a problem with, say, one of our raw binary files, we can still access all of the other binary files using the HDF5 external data writer. What this does is it allows us, it ends up with a much more fail-safe use of HDF5 files than if you use the HDF5 data writer. I should point out that from the user perspective, you only interact with the HDF5 file using the exact same interface. So you'll see there'll be a lot more files hanging around because you have a different file for all of these different, you have these raw binary files, but you essentially have the same sort of number of bytes of data, and you access them essentially the same way. You have to make sure you keep your raw binary files around and keep them in the same place relative to your HDF5 file. And you can't rename your raw binary files because all that information is encoded in the HDF5 file. And so that it works very well. That's what we've been using for all of our benchmarking simulations, is this external HDF5 data writer. And this is discussed in the manual as well. Another difference in terms of running on a cluster is your standard output and standard error files are almost always written to log files. You won't be sending that information to the screen because that information is being generated on these different compute nodes, and usually the batch system will have control of where that log file is. Usually it's not even in your local working directory. When you're running on a cluster, it's very important to consult your system administrator on MPI parameters. There are sometimes multiple avenues and choices for how the compute nodes communicate with each other. You may have a high-speed network through InfiniBand, as well as sort of the low-speed regular gigabit connections, and you want to be using the fastest available network connections to reduce the amount of time spent communicating and getting the best scalability. Your system administrator may also have installed different versions of MPI, and there may be one that others have used and found that works much better due to that particular implementation, how it's been optimized for your hardware. If you're running at a supercomputing center, be sure to read the Getting Started guides. In supercomputing centers, there's almost always multiple compilers installed, multiple versions of MPI for each of those compilers, and there's sometimes a preferred version, both sort of version as well as implementation for that particular hardware. And so you want to take advantage of that. That's usually mentioned in the Getting Started guides. Sometimes you may need to write to the system administrators to sort of get their take on what works best. And so you want to ask the system administrators and look in these Getting Started guides for what compiler suites and MPI versions are available, what file systems are available. Large computing centers, usually your home directory will be sitting on one sort of file server. There'll be scratch space that is cleaned up, say, within, files may only be able to sit there for a few hours or days at a time. And then there may be some other place that has a little with longer term storage. You want to know which file systems are available, where should you be putting your temporary files, and which support parallel input-output. You want to be writing all of your data, your output files to file systems that support parallel input-output if available. If you have a small cluster with, say, less than a couple hundred cores, or even a few, several hundred cores, usually can get by with just a file system with a fast RAID. It's only when you get sort of up to the several hundred, sort of on the upper hundred of cores to, say, 1,000 cores that you need a parallel file system. So some hints for running on the cluster. People often ask how many compute nodes and cores should I be using for a problem. In general, if you have n compute nodes and want to be running multiple jobs simultaneously, and memory use isn't a problem in terms of running out of memory, then just take the number of compute nodes you have and the number of jobs and spread them across your jobs across those compute nodes evenly. As I mentioned, you don't want to overload any compute node in terms of exceeding its memory available. You also want to be attuned to the fact that how does your queuing system, if you're not using all available cores on a particular compute node, is it going to stick another job next to yours on a compute node? That's one reason to take advantage of all the cores available, just so that you occupy all of that compute node. Similarly, sometimes you have sort of a hierarchy of sort of compute nodes in terms of how they're, what the topology of the cluster is in terms of communication. So if you have very good, fast communication between, say, every groups of 4 compute nodes, then you often sort of want to bundle your jobs into an integer value of that very tight, fast communication. Similar to the fact that now we often have multiple cores and even multiple processors on a single motherboard. In clusters, sometimes you have several compute nodes connected very tightly together in a super fast network, and then sort of multiple of those are connected in a slightly slower network. Also, when you're running at a supercomputing center or even sort of a large department cluster, you may have multiple queues that are available, usually queues with a shorter maximum runtime, such as like maximum job time of 2 hours or 6 hours. The jobs will proceed faster through those queues than queues that are allowed that may have more processors but allow jobs to run much longer, such as 12 hours or 24 hours. So you want to think about on how many processors will your job fit, and then pick the queue that's going to give you the shortest wait in terms of the time when you submit the job till when you get the results. And if you're using, say, a department cluster that doesn't have parallel input-output, but it wasn't quite designed for jobs to be using all of the cores available with that file service running in parallel, you need to be careful and only run on a small number or a fraction of the number of cores so you don't overwhelm the file servers. In quasi-static problems, as we'll see, the memory use and runtime depends on the solver parameters, and so you want to make sure that those are optimized. Take advantage of the discussion that Matt presented yesterday, or 2 days ago, sorry, on the solver parameters and making the best use of those. In most cases, for the scalable solvers, the memory use is going to be dominated by the sparse matrix. Another thing to keep in mind, especially as you scale up your problems, is that if you change the bulk rheologies, the highly nonlinear rheologies need state variables and sometimes several state variables. So they're going to use more memory than just the elastic cases. They have more parameters as well. So you add in more parameters, more state variables, and they're going to be using more memory than what the simple elastic properties with 3 values and no state variables. Dynamic rupture problems, the bulk rheologies also applies. We don't store the sparse matrix, and so we don't have as much of an issue. Also, another thing you find is that if you try and run a dynamic rupture problem with a very large fault, because it needs state variables for the fault constitutive models, it's going to use more memory than a prescribed slip problem. If you're doing a quasi-static problem with fault friction, then because your sparse matrix tends to dominate, this isn't quite as much of an issue. Let's look at some performance tests that we've done with Pilot running on a cluster. And this is the problem that we used. It's a simple static problem with slip on 3 faults. So we wanted to set up not just 1 saddle point, but 3 saddle points in this problem to really stress the solver and test the preconditioning. These are and this is included in our JGR paper that recently came out. And here's our Pilot performance test. Here's our additive Schwartz preconditioner. We did 3 different problem sizes, so I believe each one of these is increasing by a factor of, we go problem size 1, we double the problem size when we go to S2, and then increase that by another factor of 2 when we go to S4. And so you see that for both, we get relatively the same values, but not quite the same behavior for a TET mesh versus a hex mesh. The problem size for additive Schwartz, you'll notice that we're needing 180 iterations, and that increases up to 270, so a pretty significant increase in the number of iterations. When we do the sure complement with the full factorization, we get sort of particularly for hex 8, we get just a small increase in the number of iterations as the problem size increases significantly. When we do the upper factorization, sort of similar behavior, perhaps a little bit better. Now then we compare that to our field split with the additive combination. Notice that this performs not only a lot of iterations, but we get a big jump in terms of the number of iterations for the problem size, not as significant for the hex 8. So you see with the unstructured mesh, we're getting sort of the field split preconditioning with algebraic multigrid. The unstructured mesh, it's having trouble figuring out how to get a really good approximation at the coarser levels compared to the hex 8 that has a much more regular structure. Field split multiplicative combination, you'll see our number of iterations doesn't improve very much. However, when we combine our multiplicative combination with our custom fault preconditioner, we're getting some of the best performance results. And so in terms of really robust, well-tested, our field split with the multiplicative combination, custom fault preconditioner, is currently, I would say, our best performing, most robust set of solver parameters. We have yet to run this particular problem with the set of solver parameters that Matt discussed in the solver07.cfg file. And it'll be, my guess is that it's going to come in pretty close to this. and then we'll be looking at, in terms of, it may have slightly fewer iterations, but then we have to be looking at the runtime and sort of the computational effort per iteration. I think that this particular case is going to be very competitive because each iteration still goes quite quickly. Now let's look at that. So that was looking at just the comparison of the different preconditioners. Now let's look what happens when we increase the number of processors. So and the problem size. So we're looking for flat results here in terms of, this is a weak scaling. So as we double the number of processors, we're doubling the number of degrees of freedom in the problem. And so here the right panel shows our number of iterations as we go from one processor on the left side all the way up to 96 cores on the right side. So this shouldn't be labeled number of processors, it should be labeled number of processes. Sorry about that. The triangular line symbols are reflective of the TET4 case, cubes for the hex 8. So it takes a few more iterations for the TET mesh compared to the hex 8, but they're tracking each other. And for nearly a 2 orders of magnitude increase in problem size, the number of iterations is about a factor of 4 increase. So very good scaling in terms of the number of iterations. We'd like to have that perfectly flat. We're not quite there yet in terms of our solver selection. On the left-hand side, we break down where the time is spent in the solve. So on the bottom, the purple symbols indicate reforming the residual. So you see we have almost a nearly completely flat. There's some undulations in here. These problems, simulations were run on Lone Star at the Texas Supercomputing Center. There's other jobs that are running, and so we get some variation in terms of what other job, how much communication it has compared to how much communication we're doing, whether we're trying to communicate at the same amount of time, and so forth. And that's more prevalent here in the Jacobian, where there's certain cases, such as this case and this case, that we're running into a little more traffic compared to, say, this case or this case. But generally, we're seeing very flat, so very little increase in runtime for 2 orders of magnitude increase in problem size. Here's our solve. So we compute the Jacobian, we compute the residual, then we say, PETSI, please solve this linear system for us using the field split with the algebraic multigrid and the custom fault preconditioner. And you'll notice that there is some of this increase in runtime is related to the number of iterations, so our slow increase in the number of iterations, but that even when you account for that, the time per iteration increases, and we have pinpointed this to some issues with the scalability of the algebraic multigrid implementation. So we were using the ML Trilinos implementation for this particular case, and so we can switch and try one of the other algebraic multigrid algorithms within PETSI and get feedback from the rest of the PETSI development group besides Matt to sort of see, how can we improve, where's the bottleneck in terms of the scalability of the algebraic multigrid preconditioner. But in general, we're very pleased with these results, and we expect that even on larger problems, we get similar types of performance. We now want to look at the PETSI log summary and sort of show you where the time is spent on large problems in a quasi-static problem and how it differs in a dynamic problem. So on the left-hand side, this is our Savage and Prescott time-dependent viscoelastic benchmark that's included in both the pilot paper as well as discussed in the pilot manual. And you notice that 85% of the time is spent in the solve. There's about 5% of the time spent doing output. That's the post step. There's a little bit of time, 2.5%, computing things like velocities, updating displacements after we have the solution increment, and 5% is spent in the reform residual. So you'll see that with 85% of the time spent in the solver, that our solver parameters really do matter. And we can optimize the rest of Pilot as much as we want, but it's really the PETSI code that is going to control the runtime of our simulations. So we don't want to spend a whole lot of time optimizing various parts of Pilot when we really need to be hammering on what solver parameters are going to give us the fastest convergence, fastest runtime, and that sort of is indicative of why we spent a whole session talking about solvers for quasi-static problems. On the right side, I show the results of the rate and state dynamic rupture benchmark within the Southern California Earthquake Center suite. In this case, because our solve is trivial, we don't even separate out the solve. We don't even have a separate solve stage. Instead, it's down here in our step stage. So that's the solve part, and reforming our residual accounts for 59%. So while in the quasi-static reform residual account for 5%, now in our dynamic solve reform residual, and it's specifically the elasticity portion, contributes to 59% of the runtime. So that has led us to spend a fair amount of time looking at each part of our reform residual routines and really trying to pin down where the bottlenecks are and try and improve that performance. Because we can get better performance just sort of optimizing the implementation, optimizing the data structures a little bit, tweaking the functions that are called, it'll have a significant effect on the overall performance. And that's one of the things we're doing right now for version 2.2, sorry, not 2.2, 2.0, is we've seen some bottlenecks with our data structures, and so we're rewriting some of the functions to improve their performance. Looking at another part of the PETSI log, if we look at it for these across large runs of our weak scaling, as we increase the number of cores and increase the problem size, we can look at how many operations we're performing per second. So this is millions of floating point operations per second. This is the PETSI routine vec mdot that's doing the vector dot product. There's also a vector ax plus y and vec max plus y. And so you'll notice that as we go from 1 core to 2 cores, we get almost a factor of 2 increase in the number of floating operations per second. So that means we're getting great scalability. As we jump up to 4, we get, not quite a factor of 4 or another factor of 2 increase. Then we jump up to 6, and you'll see we got just a very modest increase in the number of floating point operations per second. And it's here where we're starting to run into this memory bandwidth saturation. So as we use more and more cores on this particular compute node, which has a total of 12 cores, basically the cores sit idle as they wait for values to be transferred to and from memory. So they do their calculation, they may have to sit for just a few very small fractions of a second, waiting for the values to come in from the next page of memory. And so you'll see that then as we go from 12 up to 24, so now we're using 2 compute nodes, we get a near doubling of the increase in floating point operations. Now it goes from 24 to 48. We get a near also additional factor of 2. So we're up to 20 gigaflops for 48 cores. We notice that the load imbalance is ever so slightly increasing, and that's contributing to the sort of, as we go to 96 cores, this load imbalance is a significant contribution, as well as sort of other processor communication that limits the total number of flops that we're getting. This is a vector dot product, and so we have to, when we have some nodes, remember we're dividing up our problem in the volume of the domain. So when we go to 96 cores, some processors are going to be sitting next to the faults. some processors' domains are going to be out near the boundary. If they're out near a corner, we may have multiple Dirichlet boundary conditions that are removing degrees of freedom from the system, and so their vector dot products may not take as long, whereas others don't have any constraints, so they have more degrees of freedom. And so we balance things in terms of the number of cells per process, but not the number of degrees of freedom. And so this is affecting our load balance and our ability to scale. And it's sort of something that you just pretty much have to some extent, you have to live with, because you don't want to be sitting there trying to re-optimize your code whenever you change your boundary conditions in terms of the numbers of degrees of freedom you're constraining in one problem versus another. You'll notice that as we go to this bottom, this particular operation, we see the same sort of saturation within a node, but then we're getting better scaling as we go because there's less communication and less bottlenecks in terms of even though we have the same sort of load and balance, we're not getting quite the same number of the same bottlenecks in our scaling. And by changing the solvers, you change sort of which of these low-level routines are calling, and so that'll affect the scalability of the solve as well. And so a couple more comments, specifically in terms of the parallel performance in version 1.9 versus what we expect in our upcoming release of 2.0. As in both cases, reading the mesh by a single process limits the size of the calculation. So in version 1.9, instead of going back to, say, about version 1.7, so that's about 2 years, the last 2 years we've been running dynamic problems with more than 50 million cells. So that's, if you're looking at wave propagation on the order of a period of 2 seconds, you can do sort of a 300 kilometer by 100 kilometer size mesh. If you're doing sort of very much higher resolution, then you sort of scale things back. For our SCEC dynamic rupture benchmarks, we're going into a few hertz resolution on domains that are about 60 kilometers by 60 kilometers by about 30 kilometers. We found with these older data structures, there's memory imbalances with large problems with dynamic rupture by about a factor of 10. So some processes are using 10 times as much memory as others. Part of that's because some have a lot more chunks of the fault than others. But it's also related to our sieve data structures that were not optimized for memory use. One of the big improvements in Pilot 2.0 is our improved data structures. Now that Matt knows all the different types of features that he needs to support, he has been able to develop much more optimized data structures that reduce the amount of memory, and so that alone gives us memory balancing, but it also reduces the memory use. And so that's going to allow us to run larger problems. So with better memory balancing, lower memory use, we expect in 2.0 to be able to run problems on the order of 100 million cells, or even several hundred million cells, even though we're still limited by reading in a process, reading in the mesh by a single process. So running a pilot on a cluster, you must build pilots from source in order to be able to use the multiple compute nodes on the cluster. We have developed a pilot installer that builds pilots from source. It downloads all the dependencies and builds them. You can select which dependencies are needed, so you can develop from sort of, if you want to build from pilot from source on your desktop, especially on a Linux machine, you probably have several dependencies already installed, and so you don't need to build those. And so you can select or essentially deselect those dependencies. On a cluster, you're going to want to use the MPI that has been installed by the system administrator for that hardware. So you don't want the installer to be building MPI. And when you configure when the installer configures, it's going to check based on the things that dependencies you've enabled and disabled to make sure that it has at least some confidence that, for example, that you have MPI installed if you've told it not to install MPI. The reason for developing the installer to have it build the dependencies is that this ensures that the versions of the dependencies and their configurations and builds are consistent with pilot requirements. We need all the dependencies to be built with the same compilers as well as the same compilers building pilot. And that's very important, and you can get some really strange bugs if you end up mixing compilers that aren't quite binary compatible. And if you're going to build pilot from source, there's a very extensive discussion of warnings and things and the steps involved in the install file in the installer tarball that's available on the pilot webpage. So let's look at using a queue system with Pilot. As I mentioned before, Pilot can submit directly to a queue system. In doing so, it first does some minimal validation of the simulation parameters. One of the things you don't want to have happen is your job sits in the queue for, say, several hours. It then is ready to run, and you realize you made a typo in one of your parameter files, and causing it to immediately stop and abort, and then you have to resubmit and wait another few hours for the simulation to run. One of the things Pilot does is it's going to do some minimal validation to make sure all of the prior parameters are consistent in terms of you don't have missing file names for things like spatial databases or your mesh file. File name is not there. Or unknown misspelled components, things like that. And so it'll do that before it even submits the job to the queue. Then it's going to create a shell script to submit the job, so you don't have to mess around with creating that shell script. And then it'll submit that shell script to the queue system, and then your job will sit in the queue and then run, and then you'll end up seeing the results. This whole system runs on the assumption that you've already set up running jobs on your cluster, so that sometimes you have to set up an SSH key to be able to log into the compute nodes without a passphrase, and you want to set that up so that you don't have to, because that's not included, I should mention. Sometimes you'll see various clusters, they'll have you do sort of a temporary passphrase, and they'll put that all in a shell script. So it'll be like 30 lines in a shell script to set that all up. But it's really, if you have a private key that's just on your cluster, logging in from the front end to the compute nodes, that's secure, and then you can take advantage of Pilot being able to submit the jobs directly to the queue system. So now I'm going to go through how to set up the queue parameters for the PBS queue system. This is a very commonly used queue system. It's also sometimes the open source version, or versions are known as Torque and Maui. And so from here on down, the rest of this slide is my parameters. And if you're using these same parameters, rather than putting them in your pilot app.cfg file all the time, you can stick them in a .pyr pilot app.cfg file, and this file is automatically read in every time you run Pilot. So it only applies if you want to use this queue system every single time. On a cluster, that's generally true, but you don't want to do it on your desktop machine for say things that are specific that you may be changing. And so in this particular case, we're going to tell it we're going to use the PBS scheduler, and then our scheduler component, we're telling it we want it to create a bash shell script. And then this line down here is PBS, the job submission command is qsub. And so we tell it what options we want it to pass on to qsub. In this particular case, I'm going to pass on my environment variables to the batch job. And then I want it to send me a mail when the job begins, that's the B, the job ends, that's the E, or the job aborts, that's A. And then I'm going to tell it to send the address to use when you're sending that mail. In this case, I've said johndoe@university.edu. Then I need to tell it how to launch the job. I'm going to launch using how to run in parallel, and so the command is npi run, np for number of processes. This is variable nodes that will be set by the PBS system. It's going to have to get a list of the MPI implementation needs a file that contains the particular compute nodes on which to run. That is automatically generated by the PBS system, so I just give it this variable. Normally, you'd have to be putting this in your shell script anyway, pilots will take care of this, and the PBS system will take care of that variable. So one more slide here before we run in parallel on a cluster. So a few additional parameters that I put on the command line because they are job specific is the number of nodes. That's the total number of processes I'm going to use. And then for PBS, you give it the processes per compute node. So that's PPN. And so the number of compute nodes that I'm going to be using is my total number of processes divided by the processes per node. So you want to make sure that your number of total processes is exactly divisible by your processes per node. You can give it the job name. This is the name that's going to show up in the queue system. And in your log file, you can give it your standard out. You tell it the name of your log file. The default is just standardout.txt, I believe. And some schedulers will allow you to combine standard error, standard out. Sometimes you want to separate them. And I tend to keep them separate, so that way I see the errors separately and from all the verbose output that I generally have with the pilot, where it's telling me where I am in the file or where I am in the simulation. Are there any questions up to this point on sort of using the queue system? We're going to, in a second, we're going to actually run through a hands-on example of using it, but any sort of general questions about running on a cluster and using a queue system? Okay, I don't see any questions, so let's switch now.